Hi there and welcome to our first lesson in our C3 topic all about chemical economics. Now our first lesson is going to be on rates of reaction, and if you've had a look through you'll see that the first three lessons are all about rate of reaction. Now what we'll do is I've split it down into three, and we're going to start with rates of reaction 1, and here are our objectives. So our objectives for lesson 1, rates of reaction 1, is by the end of this lesson you should know and understand what the rate of reaction of a chemical reaction is. Chemical reactions have a rate. Now the rate tells you how fast it is. Now some reactions happen very slowly, such as rusting, whereas other reactions can happen very quickly, things like explosions. Now we can actually have a look at a set of results here that show how the reactions can actually change. Now in this set of results we've got a concentration here. Now as you notice we increase the concentration. Now what happens is as the concentration gets bigger, the number gets bigger, the time for the reaction takes less, or it gets smaller. Now this is because the low concentration we have a low reaction time. That means the rate is a lot slower, whereas when we get to the top we've got the faster reaction with the higher concentration. Now in an exam situation you might be asked to plot a graph showing these results. Now I'm just going to adjust a few things on here, so let's move that up to here. Now with a graph you might have to plot something that looks like this. Now if we are to take concentration is something that we have changed, so that would always go along the bottom. Now anything that we measure would then go across the side, along the side. Now as the concentration increases, the time for the reaction gets less, so we would have a reaction or graph that looks like this. Now we then have to use this data to find out what, for example, what the result might be for a concentration of 0.03 m. Now obviously the value is between this value here and this value here, so what we would do is we would find where it is, and we go up and we'd use the graph. Now I've not drawn that very carefully, so let's just adjust that to here, and that would give us a time. Now we can see by the data that we've got that it's between 72 and 33, so we'll be looking roughly at a number around 52 seconds. Now you don't have to have amazing levels of precision with this, but it does help to get your graph as neat as possible so that you can get that key result. Now with the set of data that we've just seen, we've actually carried out an experiment where we have added some magnesium to some acid. Now what will happen is the magnesium will react with the acid and will eventually form two products. Now those products will be a gas, hydrogen gas, because we're reacting a metal with an acid, and a salt, which would be magnesium chloride. Now you have to excuse the subscripts, but the 2's should be lower than, or a smaller font, but unfortunately I can't do that. Now we can tell that the reaction is finished because there'll be no more gas being given off. Now this means that either one of these has run out. Now the likelihood is that when we do this in school it's going to be magnesium. That means magnesium is what we call a limiting reactant, and that means that it will run out before the other one, so that has the effect on the rate of the reaction. Now, the amount of the limiting reactant that you have, in this case magnesium, will result in or dictate how much of the two products you get. Now, with this reaction, because hydrogen is a gas, you're going to likely to be monitoring how much gas is being given off as to when the reaction will finish. Now, when the magnesium has run out, no more hydrogen gas will be produced. So the amount of the limiting reactant will dictate how much of the product will actually be made. Now, whenever you have a reaction that involves a gas, there are two ways that you can actually monitor the reaction. Now, the first way is where you actually monitor the amount of reactant that there is. So if we have a look at this equipment here, you can see that you've got the solid here, so it could be magnesium, it could be calcium carbonate with an acid. Now, as the bubbles are given off, the bubbles will no longer be in the reaction and they can actually escape through the cotton wool, meaning that there is less of a force of gravity pulling down on the mass, so therefore the mass, the values on here, will increase. Alternatively, you can actually monitor the products. Now, if you monitor the products, again, with a gas reaction, you are going to have a gas given off. Now here, you've got the reaction, you've got the solid in here, and here you've got a delivery tube that will go into here we've got a gas syringe that you can monitor the volume of gas that's given off. Now, a gas syringe is quite a precise method of actually collecting results. You could use a measuring cylinder or you could use a burette that's been inverted. Now, with these types of reactions, what you are doing is you are monitoring the reaction after a certain period of time, and you continue to do that. So for example, you might do every 30 seconds for 5 minutes perhaps, or 3 minutes, and you take a volume of gas. So you might find that the gas after 30 seconds is here, and then after 60 seconds it's here, and so on and so on. Now, what we'll have a look at in a moment is what we can do with that data. Now, what we're going to do now is have a look at a set of data. So we've got a set of data here where we've got the time that we've taken a volume of gas. Now, we've recorded the volume of gas at two temperatures, at 50 degrees and at 25 degrees. So we've got this set of data here, and then we've got this set of data here. Now, I'm going to get rid of this data, okay, and I'm going to draw a set of axes. Now, on the x-axis is something we have controlled, and we have controlled the time, and we've done that in seconds. Now, on the y-axis, we've measured the volume of gas, okay, and we've done that in centimetres cubed, okay. Now, I'm just going to adjust this slightly here. Now, if we were to plot, I'm going to delete that line because it's not very straight. Okay, if we were going to plot our data, what we would end up with is we'd end up with a graph initially looking like this. Okay, now if we were to show the second set of results, it would move along like this. Now, if we show the results again here, okay, we can see that for both of them, the maximum they produce is 62 centimetre cubed. So along this line here, this is where we actually get to 62 centimetre cube, and that's where the limiting reactant actually finishes. Now the other thing we can see is at this point here, that's when the first reaction finished, and then at this point here is when the second reaction finished. So we can see that we've got two different times at the two different temperatures. Now this is where we start to get quite clever and quite technical. Now because we've got a curved line here, it means that we can't work out a gradient. Now what we can do is we can actually work out a gradient by drawing what we call a tangent line, and that is where we have a line that goes around or up from that initial point. Now from there we can actually make a square, and we can work out what the angle is of that line, and therefore we can work out our gradient. And the gradient is equal to the length. Now to work out the gradient is equal to the value of y over the value of x. And that is taken from the value of y here against the value of x along here. So whatever this value is here over this value here will give you your gradient and therefore your rate. Now what you'll also notice is that as the graph goes along, the angle of our tangent line actually gets shallower, and therefore the rate actually slows down. Okay, so that's the end of our first reaction, where we have been looking at rates of reaction. We have looked at how the rate of different concentrations can change and how we can measure that, so the time for a reaction to finish. We've also looked at the limiting reactant that suggests what might control when that reaction finishes. We've also looked at how we can measure the reactants that are lost, or we can measure the products that are produced. And then we've looked at some data that shows how reactions might change over time. Remember that most reactions will eventually get slower. Anyway, I hope you've enjoyed this, and I will see you next time. Take care. Bye-bye.